Good morning and welcome to the third in the series of 5 webinars on the Catalyst project. This is a rerunning of the webinar from last Wednesday, which we had to rerun because of technical problems. My name is John Booth and I'm the project lead for Green IT Amsterdam, and I'll be your host for the entire series. Our project coordinator has recorded an introduction and overview to the project, and we'll start with that in a moment, followed by our colleague Ariel from the Ponson National Supercomputer in Poland with an overview of the Catalyst pilot sites. We'll close with some questions after that video. Hey.
Hi, I'm Diego Arnone. I'm a project manager and I'm a senior member of the Research and Development Laboratory of the Engineering Group. And in the role of coordinator of the Catalyst project, I'm going to give you a bird's eye view of this research initiative co-funded by the H2020 Framework Program. This introduction explains at a very high level what the project has developed and what kind of benefits it aims to achieve. Let's start from a proposal. Well, we are in the context of data centers connected to more commodity networks like power grid, data networks, district heating. The proposed idea is that data centers can and should offer energy flexibility services to their smart grid and district heating networks. So data centers should not be considered as only as energy consumers, but as active players that are able to sell their intrinsic flexibility. This is the identity card of the project. We have close to 3 million euros assigned to a consortium of 10 partners based in 6 European countries. 3 of them are industrial partners, the coordinator engineering, Singular Logic and Schubert Phyllis. 2 are small medium enterprises, PowerOps and Carnot. 2 are research institutes, PSNC in Poland and University of Cluj-Napoca in Romania. 2 are utilities, NLX and Alliander. We have 4 data centers that are our workbench for the validation. In the Catalyst vision, data centers are to be intended as multi-carrier hubs that work at the crossroad of more networks, energy networks and data networks. And these hubs can exploit and manage their intrinsic redundancy to provide flexibility, to deliver system-level multi-carrier flexibility services. The consequent new revenue streams can allow them to invest in energy efficiency and in reducing data centers' environmental footprint. This figure depicts the concept of the project. A data center, thanks to an innovative resource management and optimization system, is able to sell flexibility to the local DSO, the distribution system operator, by putting offers on a local balancing marketplace in order to sell or buy energy, both electricity and heat, in another marketplace, or to move IT workload from a data center to another federated one. We must think that a data center consumes energy to supply servers that execute workload and generate waste heat. So power, heat, IT workload are strictly linked to each other in a data center. These commodities can be traded in a multi-flavor coupled marketplace that Catalyst proposes as a service. The flavors are electric flexibility, electricity, then energy, heat, IT workload. And this picture shows how a data center stays in the middle. So, in conclusion, electricity, heat, and IT workload are considered as commodities that can be traded, exchanged, transferred in their corresponding emerging markets, either individually or combined to achieve synergies whenever possible. In order to achieve its own objectives, Catalyst has not started from scratch, but this project has merged, evolved, extended, and also integrated the results coming from Geyser and Dolphin, two FP7 research projects successfully completed by some of the partners involved in Catalyst. The new developed tools can utilize and trade the waste data center heat to lower the overall system level energy distribution footprint, reduce data center energy costs and create new data center incomes, can assess resiliency of energy supply and flexibility, trading off data center assets against local distributed RES, energy storage, and efficiency, can deliver energy flexibility services to the surrounding energy grids ecosystems, can also exploit migration of traceable ICT workload among federated data centers, matching the IT workload demands with time-varying on-site RES surplus availability or where heat generation is needed. This is the follow the energy approach. These tools have been developed to be adaptable to a variety of data centers categories. Different types, colocation, enterprise, HPC, different geographical location, different architecture, from large centralized to fully decentralized micro data centers. As already mentioned, Catalyst is validating the main results of the project in 4 different pilots. The green geothermal co-location data center in Ponson in Italy, owned and managed by the engineering group, the coordinator of the project. HPC data center based in Poznan, Poland, partially supplied by renewable energy sources, that is experimenting the reuse of waste heat by heating up a building of the nearby university campus. A fully distributed data center operated by Carnot, where servers are installed in different buildings as heaters. A co-location data center owned and managed by Schubert Phillips, integrated with a smart grid. They are experimenting the provision of electrical flexibility to the grid. There's also a legacy data center operated by Singular Logic, but used only for lab experimentation. Okay, this card shows the list of the core features of Catalyst that are being validated. So free air and water cooling, geothermal and passive water cooling connecting to the drinking water grid. The first one is tested in the engineering Ponson data center. The second one in Schubert Phillips, the Netherlands, in collaboration with Oleander. Waste heat regeneration via heat pumps and reuse of smart thermal low temperature district heating networks. This is happening in Schubert Phillips and Poznan. Also space heating, cooling of colocation data center offices in favorable seasons. So Ponson colocation data center in alpine climate area in Italy, but also Poznan and Schubert-Phillips. Smart waste heat reuse and preheating diesel engines and UPS systems, so Schubert-Phillips, the Netherlands. And RES, basically photovoltaic panels, and DES, basically batteries, integration, this in Poznan. Heat demand driven IT workload balancing in a fully distributed data center. This is the case of Carnot in France. Energy flexibility services via backup generator. So battery storage, UPS, and flexible workload adaptation of IT workload. And this is happening in Poznan and Schubert-Phillips. IT load balancing, targeting lowering of energy consumption and cooling needs between legacy commercial data centers belonging to different administrative domains, for example, singular logic, and green data centers, so engineering Ponson data center or Poznan. Last but not least, the value proposition. This nice picture shows the benefits for data centers because this technology reduces the operating costs for energy, is able to improve performance and creates new revenues by reusing waste heat and by providing flexibility services. The energy sector, because we have a better stability and security of supply, easy access to local flexibility services, accelerated heat reuse, but also for smart cities, especially by empowering energy prosumers and unlocking their flexibility potential. So, we need interested partners, people interested in this new idea of data center to be intended as active player in the smart energy infrastructure of the future. So become the catalyst to energy transition, support green data centers in Europe, join the Green Data Center Stakeholder Group. What you need to know is in our manifesto that can be downloaded from the website. And this is how you can join us. That's all from my side. I hope that this short introduction will be useful for a better understanding of all the tools that have been developed and will be explained in the followings. So, enjoy your webinar. Goodbye.
Thank you, Diego, for the overview of the project. And now we'll move on to the next part of the presentation, which is the Catalyst pilots delivered by our colleague Ariel at the Poznan Super and National Computing Centre. Off we go.
Welcome to the next Catalyst webinar. My name is Ariel Leksiak from Poznan Supercomputing and Networking Center, and I will introduce Catalyst pilots. The pilots that use and test Catalyst approach methodologies and tools. So there are 4 main pilots in our project, which are quite different data centers. We have a complementary data centers to test project solutions. So the first one is engineering, which is a colocation data center and owned by engineering company. And what they what they do in the project, they try to use the thermal inertia of cooling, and also they have diesel generators that can be applied in maintenance periods for flexibility. PSNC is a high performance computing data center, which is it's a bit different applications. It applies liquid cooling, already use some heat reuse in its offices, and have some photovoltaic system on site. Another colocation data center is Schubert-Phillips, and the fourth one it's totally different data center, which is a distributed data center run by Carnot, where IT load is executed in distributed geographically servers. What is quite important in Catalyst, as you already heard, that Catalyst is not focused only on providing electrical flexibility, but also taking into account IT load and heat. This is quite important. So that's why we also consider scenarios like the reuse of waste heat at Catalyst. So, for instance, at PSNC, HPC data center, or the heat is already reused in the office or in our building, but we are looking into applying the waste heat in external buildings, in other outside our building. Carnot, of course, as this is distributed data center, and the servers are producing heat that is directly used by customers. So this heat reuse is at the core of Carnot business. And then PSMDC, owned by engineering, and Schubert Phillies, they have also plans for the use of waste heat in their office buildings. Another important point, as I mentioned, is that we also consider electricity, heat, and IT load. So also we have trials where pilots try to experiment with federated IT load balancing, and we'll show the scenario where the load from Carnot, normally executed on distributed servers, is migrated to regular data centers like PSNC, and PSNC is one of the data centers receiving the load, so providing resources, and we study what is the results in terms of efficiency and the use of energy. And then Schubert Phillies also is a data center that received the migrated load, and that in PSMDC the marketplace is installed. So once again, to summarize how the Catalyst pilots are complementary to each other. So because we consider electrical energy, thermal energy, and IT load, the flexibility techniques are various, let's say. So first of all, we adapt the IT power by shifting or migration the delay tolerant load, so the load that can be shifted, can be postponed. We also can apply techniques like reducing the power by using power capping on servers. So also that means that some load can be a bit delayed, but the power is lower. And in addition to IT power adaptation, we also we use the inertia of cooling systems by changing temperature settings or even switching off the cooling. The use of energy, renewable energy, and energy storage can be applied, or even use of generators in maintenance periods. So these are actions that could be used and are tested in the pilots. So let's go to the first pilot, which is Green Ponson Martin data center, owned by engineering company. So that's one of the 4 engineering data centers, and also it's one of course of the 4 pilots involved in the Catalyst project. The data center is 1 megawatt colocation data center, and it's the most relevant data center for engineering. It was upgraded over the year, and both from technological and security point of view. And a new important refurbishment of data center cooling system is planned next year. So the new cooling system is designed to mainly exploit the available groundwater in order to satisfy all data center needs, considering also possible future expansion of the data center. So what are the main trials within this pilot? So the pilot focus on two main flexibility resources. The first one is the inertia of cooling system, the refrigerating units. So the thermal inertia of cooling pipes is kind of, we can think of it as a virtual thermal storage, and that was used in the trials, and the trial proved that for around 26 minutes, almost to 100 kilowatts exploitable flexibility was provided thanks to this approach. Diesel generators, as I already mentioned, of course they produce some emissions, so we need to be careful about this. But in Ponson there are some maintenance periods where maintenance tests when these generators are switch on anyway. So in this case, they can be used for source of flexibility, and even providing 1 megawatt flexibility for the whole data center. So, of course, to proceed with the trials, the Catalyst tools were deployed in Ponson data center, and that these tools are responsible for monitoring of relevant measurements made available through an OPC server. And the monitoring system interface gathers data on power consumption of refrigerating units and the IT power demand, and then these data are stored in the Catalyst database. And then where the data model defined in the project is also stored. And another action that is done by this software, these tools, is the optimization and the computation of optimization plans. And this is performed by DC energy flexibility prediction optimization tool. And static and real measurements stored in the Catalyst database are therefore processed in order to identify the flexibility actions that are shown to the DC manager for the formal approval. And the third important functionality is that the automated participation of the data center to the Catalyst flexibility marketplace through the marketplace connector takes place. And of course, as I already said about the potential actions, the optimization plans consist of several actions that suggest to the data center an efficient use of its own resources, and propose to buy or sell energy, electricity or heat, electrical flexibility or IT workload, and by submitting proper bids and offers on the marketplace. So, just to summarize, the main goal was to demonstrate that Ponson data center can work as a hub at the crossroad of two energy networks, power and heat. So that's the main goal, and also it's important that this approach opens the possibility to get new revenue streams for data center, not only by providing computational services for customers. And so as we can see in this trial, the Catalyst can support data center operator in electrical and thermal flexibility actions. So yeah, so these trials from Ponson were focused on the couple of scenarios defined in the Catalyst project. So first of all, providing, so first scenario one, which is single data center providing electrical energy or electrical flexibility, then single data center providing heat, and data center providing both thermal and electrical energy flexibility. So as an example of the results that were produced using the energy optimizer tool from Catalyst. So you can see the real measurements collected in the database, and historical electricity consumption, and on the right, the energy consumption split on the flexibility components. So real measurements gathered in the data center underlies the performed trial. So this data are shown through the data center operator. So data center energy consumption varies slightly around an average of more than 700 kilowatts. And so by selecting the prediction menu on the electrical energy tab, the historical and the predicted energy consumption and production are displayed. So the data center manager can compare the previous day pattern with the forecast for the next day. The prediction is computed starting from the data acquired by the data center monitoring system. Since the trial uses a hybrid strategy of both flexibility and thermal profit maximization, the forecast from both the electrical forecasting tool and heat forecasting tool is computed. So we can see at the bottom, you can see also the forecasted thermal energy generation. So this electrical and thermal prediction is one of the input of the Catalyst optimizer that computes the flexibility management action plan. This plan leverages on both shift delay tolerant workload actions and post-cooling of the server room to allow the data center to adapt both its electrical energy consumption and the thermal energy generation to match the bids and offers from the flexibility and heat markets. So the data center manager can view the optimization plan through the data center operator console, as you can see on the screen now. And the same optimization plan from the thermal perspective is shown. Thus, the data center operator can see the thermal generation of the data center by applying the same action plan, and the generated heat will be sold on the heat marketplace by placing sell heat offers. So the chart, the chart on the left shows the baseline heat generation, dark green, and the adapted heat generation, light green. And the effect of the post-cooling action on the data center heat generation can be seen by the dark blue columns from the right chart. So in this way, we achieve the flexibility by changing the periods of the extensive use of the cooling. So to summarize, the trial from Ponson Martin data center was successful and showing that the software produced by Catalyst is able to adapt both the electrical energy profile and the thermal energy profile to the needs of the to meet the specific requests, flexibility requests. And in this case of thermal, in the thermal case, the actions were simulated because it's the trial is based on some cooling system features and then heat pumps. The next pilot is Ponson Supercomputing and Networking Center, which is a bit different from the previous, as I mentioned, because it's a high-performance computing data center. It's a 2 megawatt, currently 2 megawatt data center with options to extend, and some extensions are planned already right now. The heat is already reused locally, and we have also some photovoltaic systems with batteries on site. So there are a number of trials run at and the PSNC pilot. So I will focus now on these the two first. The IT load balancing will be shown presenting the Carnot pilot. So the first one is focused on the electrical energy flexibility, and so where we are trying to adjust the IT load according to the energy optimizer suggestions. But what we do also is also we are analyzing the cooling system as a mechanism for flexibility. But what is important, we take into account the use of renewables here. And the second trial is focused on the feasibility study of the heat reuse in the campus around in our data center. So these are the scenarios that are covered, the catalyst scenarios covered by our trials. So this first trial focused on the electrical energy flexibility using photovoltaic system. So in this way, in this case, the goal is to maximize the use of renewable energy, and we'll show that the energy optimizer and the catalyst tools are able to do it. So what we are using in this trial is our photovoltaic system, from which we can use several kilowatts for servers, and we have batteries with 75 kilowatt hours capacity, and so we power part of our resources, our servers, with this system. And the actions that we consider is, on one hand, reducing the IT load, either by shifting delay tolerant load and using the function of draining nodes in the specific resource management system called SLARM, or by power capping. And of course, we use also the other actions are just the use of energy generated by photovoltaic system and the use of batteries. So catalyst tools used are, first of all, the intra data center energy optimizer and other tools integrated with this component. So we in this trial we provide the data to the intra-DC energy optimizer, such as the load of servers, the delayed tolerant load, the production of the photovoltaic system, capacity of batteries. And based on this historical data, the prediction are provided, and the optimizer tries to adapt the situation in our data center to the request. So we can see the profile that is following the renewable energy availability on the left. So the dark green is adapted data center energy profile, while the light green is renewable energy. And on the right, you can see the results based on the use of this data. So you can see in the middle of the day the use of renewable energy, and you also see the consumption of the power usage of the delay tolerant load and the non-delay tolerant load. So the light red, let's say, is a delay tolerant load. And also at night we can see the use of the batteries, the battery discharge. So in that case, some energy, which is also mostly come from the renewable energy, it's used from batteries. Of course, we need to be careful with using batteries, not to discharge them too much to the too low levels. So that's also what we consider. So for to avoid this, that's on this plot you can see the state of charge of battery, which is blue. The yellow is generation by photovoltaic system, and the red one is the power usage from battery, and then the server power consumption is green. And you can see that when the photovoltaic system is stopping the work, then we discharge batteries, and we are adjusting the discharge in such a way to avoid exceeding the 40% of state of charge, to avoid decreasing the lifetime of batteries. And we are doing it using the power capping mechanism to lower the power in a way that we don't discharge the battery. So that's in such case, in this experiment, we were able even to reach this 100% power supply from renewables. In the case where we have more servers connected, and depending on the situation, it can be about 50%. So another action that we experiment with, which we experiment, was also testing the impact of the changing the temperatures. So not switching off the cooling totally, but changing the temperatures in certain periods to decrease the power consumption by cooling system. Of course, it has some consequences on energy usage by servers. The power usage is a bit higher, so you need to find a trade-off. And but you can find a trade-off where the of course that where the gains in the use of energy are better than the losses due to leakage power. And it's also quite interesting because it has some consequences for some scenarios related to heat reuse, because the higher temperatures of the outlet from data center, then it's more usable for external heat reuse. So we need to consume less energy for increasing the temperatures, the outlet temperatures, and for instance by heat pumps. So that's also quite interesting results, especially that the second important trial is the analysis of the waste heat reuse in our data center. So as I already mentioned, we use the heat from the system with power usage around up to 1 megawatt, and the 300 kilowatt heat exchanger is used for that purpose. And but planning some new systems, we see that there will be some surplus energy that could be reused further. So so that's why we are thinking about looking into the demands of the buildings in the campus, because PSNC is located next to the Poznań University of Technology campus, and which have buildings, for instance, with some even more than 1 megawatt of heat contracted from the heat grid operator, with some usual needs which are a bit lower, or even 2 times lower. And but of course that's there are some issues with this connection, like for instance the very high temperatures of heat network, and also that there are some limited options to dynamically adapt the heat production, and so consumers would like to have some guarantees. So as I mentioned, it's so first of all, we have some heterogeneous installation, so we have different loops in at a data center, and so looking into the future installations, that we would have to use the separate loops of new systems to provide such heat reuse out of the building. And so we consider the connection to one of the campus buildings, which higher demands. And but the problem is that these demands, of course, are very different depending on the seasons. So in the winter is very high, and in the summer quite low. And if you compare it with more or less with data center heat production, you can see that during winter, it's of course the whole heat would be consumed, but in the summer there's some excess heat. So and you can see that in the campus you can see also some other sources, but I think the data center is the most important one. So the important observation, of course, was that also the temperature of heat network is lower in the summer, which means that it will be easier to provide the heat from data center to the heat network in the summer. And already we discussed it with heat grid operator, and that they would be interested in receiving the low emissions heat during the summer. So that could be the solution, that we could sell this surplus heat energy heat during summer to the heat grid operator. So we concluded with some designs and options how to connect the data center, how to provide the heat from in the winter and in the summer. So in the summer would be the connection to the heat grid operator network, which you can see on the as a pink lines on the pictures on the right, and in winter period most of all the heat would be reused. So just summarizing, so we analyze some data from existing data from several months of existing data centers, but also made some projection for new systems, and yeah, so we concluded with some idea how to connect it, how to do it, and so that we could also use the heat grid operator network, but in a way that it would be economically viable for us. And so in the results provided information that that more than 8,000 gigajoules could be reused by external buildings, and more than 27,000 of gigajoules could be sold. So that's first result. And the electrical energy consumption for heat pumps and circulation pumps would be as on the slide. So in general, that shows that this approach could be economically viable, but still further business evaluation is needed, and is done by us also in the final reports from the project. So moving to next pilot, Schubert-Phillies. So it's a colocation data center, but it takes part in the scenario with IT-load migration, as we could consider a situation where this colocation data center, let's say, have some contract to provide resources for such company, like for instance Cardinal, who needs some backup solution when he needs to migrate jobs from distributed servers. So in this case, the migration between Cardinal and Schubert-Phillies is being tested, and then the idea is that it work with IT load balancing software from Catalyst. So the test consists of the typical Cardinal server, which is a traditional air-cooled server. On Schubert-Phillies side, the Asperitas emerge server is used, which is an additional interesting case. I will come back to it later. And the Catalyst DCMC software for IT load simulation and migration is used. And the measurements on both sides were done in terms of power usage, CPU usage, temperatures, and so this data, some more information about migration will be shown during the Cardinal pilot. Okay, but maybe some words about this Asperitas server rack. So it's quite interesting case, as servers are immersed in the non-conducting fluid. So it's a kind of immersive cooling, and the natural convection is used to drive the circulation. So no fans, no pumps. So which means that it's very efficient and also quite reliable. And the server rack is installed in Schubert-Phillies site, and so it has climate independent. It's climate independent with more water cooling ability, which means that also it has high potential for heat reuse. So the water input is even 40, 50 degrees Celsius, and water output 50, 60, which is very high. And basically, if we just used such such loop with such temperature, we basically we are sure that we will have the free cooling all of the year in various locations. And also monitoring and control is integrated, and it's also very flexible for high density compute and storage solutions. So just to summarize the Kubernetes pilot, so the test on migration from kernel to Kubernetes are being done, and just to proving that that's feasible, that's possible, and provides the profits, and also to showing the difference between submerged and additional cooling, and its potential maybe for heat use. Moving to the last fourth pilot, which is very different actually from previous ones. It's a distributed kernel system, and kernel is focusing on three main scenarios. So also on electrical energy flexibility, but then on the workload federated data centers and workload federated data centers providing thermal energy flexibility. So the main goals for kernel is to handle actually the edge computing site energy consumption for heat production management and electricity demand response. So as you remember, the servers, kernel servers are deployed remotely in houses and buildings, and are used directly as a source of heat. And also the second goal is to use IT workload migration or location among data center sites for grid resilience and heat management. So if we look into the first scenario about electrical energy flexibility, so kernel also deployed and used the Catalyst Energy Optimizer with some other tools like DC operator console, energy efficiency metrics calculator, the prediction, electricity prediction, and data storage, and so on. And also used in the experiment the production HDC of more than 200 kilowatts. It's a kernel scale max. And the goals here were to demonstrate optimization plans impact and observe the features for kernel resources. So you can see the results from optimizer, where the adapted data center energy profile is suggested by energy optimizer. It can follow the demand quite nicely, but it's also because of quite high percentage of the delay tolerant workload at kernel, as you can see on the right picture, where most of the workload is delay tolerant. So that's why it gives some flexibility to the optimizer to provide the action plans. So the live production data were used for this purpose, and this action plan lead to the value of data center adapt metric of 0.71, which basically means that this high level of adaptability were achieved. So in that's possible in such case where we have this quite big part of IT load can be shifted or postponed or migrated. As said before, so kernel also focus on the scenario with IT load migration, so which between federated data centers, and for that purpose, the Catalyst tools such as the CMC server and client and CG and Slark were deployed, And this, in general, this testbed includes all pilots, but so this Antiload Migration were tested between Cardinal and Ponson Superconducting Networking Center and Schubert-Phillips data centers. So you can on the left bottom you can see the diagram with the tools installed. So you can see the sites like Cardinal and PSNC, and also there are some tools needed on the federated level. So you need DCMC server and VCG server on the federated level to perform such migrations. On the level of data centers, you need the DCMC client and some other tools, in additional tools or frameworks like OpenStack. So 3 VMs, virtual machines, were used for experimentation. So starting from some CPU burn to stress the resources and to assess the VM relocation and energy transfer, web server to access connectivity, and Blender application to assess real life IT load with some results. So it's a rendering software. So the main result was that this IT load migration and relocation were successful, done in real situation. So migration time was between 3 and 26 minutes. There were no connection losses. The virtual machines were fully responsive with some 13 milliseconds extra latency. So you can see the example here on the plot where the migration between Cardinal and PSNC were done, and then it ran at PSNC resources for some period, and then back was migrated to Cardinal. So that test was successful. What is also important in scenario 4, also this workload federation between data centers, but also taking into account the thermal energy flexibility was studied. So in this case also the stack was similar of tools, but also there was a simulated IT load migration by thermal request. So you can imagine like the temperature, the heat demand at the local site is lower, and then the power and temperatures are going higher, and then the decision about migration must be taken. So that's scenario was tested by Cardinal. And what are the conclusions then from the Cardinal pilot and Cardinal trials? So in general, the Catalyst tools are easy to deploy, assuming that some basic framework, the basic software is available, like OpenStack is deployed. Concerning energy flexibility, the energy optimization was satisfying and accurate, and both standalone and included Catalyst solution. And for IT load migration, there were good points, and results were that it was easy to perform and was seamless for user, no downtime. So it was really possible to perform. Of course, some potential issues should be taken into account based on specific data center infrastructure and let's say customers' demands and so on. So first of all, migration time depends on connectivity, and then the virtual machine activity, and also it's difficult to forecast the virtual machine energy consumption destination data center. and there's a need for full access to software and hardware. So for colocation data center, it would have to be probably the company that do the migration would have to have its own servers, let's say, in a colocation data center to perform this. Concerning thermal, we are using Antiload Migration. That was perfectly efficient, and the response time was just limited by thermal inertia, because of course it takes time to change the temperature, and migration time. So to conclude, the run of trials in Catalyst pilots and the use of Catalyst approach methodology and tools in real data centers. So we studied the flexibility for various data centers, from colocation to high performance computing to distributed ones, and there's already results, so that there was some evidence that quite high flexibility can be shown, even up to 100%, depending on the action applied, and which are of course depends on the infrastructure and types of load and the percentage of delay tolerant workload. But first of all, the results shows that there is a very high potential in combining these three aspects, like IT, load, electricity, and heat. And we also included the heat reuse scenarios, which also has very high potential, we think, for data centers and other systems and other industry. So the next step is that we now finalizing some business models. We finalizing the reports where we define how that could be used and profitable for data centers, and also trying to define some recommendations and guidelines for other. Just to summarize how it can be used, what are some issues still to be solved, and how to adapt, how to integrate these tools with real data centers. So thank you very much, and if you have any questions, you're welcome to answer. Thank you very much.
Thank you, Ariel, for that very comprehensive analysis of the Catalyst pilots. Okay, so I'll open the floor for questions. Anybody who wants to raise their hand and put in the chat, I'll answer the question of Ariel, who's online as well. Okay, there's not been any questions. Last chance to raise a question, otherwise I'll close the webinar down. Okay, I'll close the webinar now with a quick reminder that we have another two scheduled. First is later today at 2 o'clock. It's the official global launch of the Catalyst Green Data Center Roadmap and Assessment Tool website. And we'll also be visiting the website roadmap.project-catalyst.eu and going through it in some detail. Next week, in association with Data Centers Ireland, we host the 5th and final session in the Catalyst webinar series and the 3rd in the Data Centers Ireland Leadership Series with a panel debate entitled Heat Close to the Edge. So join me and our expert panel on the 22nd of September at 10 o'clock, running through to about 11:30 or so. We look forward to seeing you again, and have a great morning, and I hope to hear from you and see you on the Catalyst webinar at 2 o'clock this afternoon. Thank you very much.